Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'd like to introduce the first talk today, which is Enhancing BLAST Comprehension with SilverMap. And Jim Hogan will be talking to us from Queensland University of Technology.
And my thanks, as usual, to the organisers. So today we're going to be talking about a couple of things in relation to improving the way that we look at BLAST results and making more sense of them. And in particular, trying to work with BLAST results when we're dealing with a very large number of them. So BLAST is something which I think everyone in bioinformatics is familiar with, and I don't think it's showing any sign of going away in a hurry. And it is, of course, the tool of choice for discovering similarity amongst sequences and sequence fragments when we have any significant amount of scale. Our brief agenda for today's talk then is to talk about making sense of sequences, and in particular about making sense of sequences when we have a lot of them. We'll then introduce our tool SilverMap in an earlier guise, and then we'll talk about the extensions that are the subject of this talk, which brings us to the BLAST Explorer. We'll illustrate that through the use of a fairly current sort of case study, which concerns work in leukemia, and then we'll talk about where the tool is going. So making sense of sequences, we're all familiar with this particular idea where we take a reference gene or a protein, we select some sort of target set of organisms, and we go looking for similarity from that gene or to that gene in the target set. And everyone's done this, and we get a large collection usually, or a significant collection of hits and some associated confidence, which is normally expressed as an e-value. But of course, when we start to look at those hits, they can become rather a mess. I mean, there's a large number of hits often, and certainly there's a lot of associated information with each of those hits. Now, this is both a curse and a blessing. Obviously, as a curse, these sorts of views cannot support comparative genomics on the modern scale. We simply cannot make sense of that amount of information if we then start extending the sorts of queries that we do, not merely to one gene or one protein, but hundreds of genes and proteins, and potentially dozens or even hundreds of target organisms and the thousands of genes that are associated with those. But the important point too, when we say that this is a blessing as well as a curse, is to note that each BLAST result provides fairly critical information about the quality of the hit, which we've illustrated there with the e-value, obviously, and also its context in the target genome, which is actually looking at what the match turns out to be. And many biologists of my acquaintance place a great deal more store by their observation of this particular part of the display than they do about the e-value. Many biologists have very little confidence in the e-value at all. And what we really want to do if we're going to extend BLAST and utilize BLAST is to have some mechanism so that we get the benefit of both worlds, okay? So that we actually have the facility for dealing with large numbers of genes and large numbers of proteins, but we don't want to give all this stuff up, okay? And that's pretty much the two design goals that we had in mind when we went towards the BLAST Explorer. So this is SilverMap. So SilverMap is a tool that we presented last year, and SilverMap is a tool which is designed primarily to enable you to see relationships between genes and proteins based on their similarity. And the idea, of course, was to overcome the cognitive overload of the sorts of displays that we saw before by working towards the familiar metaphor of navigation, in this case a radar display. Here the query gene or the query node is at the center. All of the other matches or hits, if you like, are organized radially around that central query node. Okay, and so what you've actually got is an e-value which is exponentiated and squashed so that we get some sort of correspondence between the e-value and the radial distance on this display. So what we see obviously are the ones close to the query node. They're the ones which are very good matches. Further out from that we start to do badly, and when we come right out here there's very little correspondence at all. The other point about this is that the map shown is based on pre-computed blasts, okay? N versus N minus 1 blasts for multiple E. coli genomes. So there are about 70,000 genes in this collection based on 14 strands of E. coli, strains of E. coli. But this is great if we have the collection, and certainly we're expanding that collection, and we have another one with human and mouse genomes. But what if we just have a single query sequence and we want to explore? And that's, of course, the other aspect of the BLAST Explorer. We want to start from a single query and work our way out. And so the BLAST Explorer takes SilverMap as its core, but introduces a couple of other features either side of it. So the SilverMap display remains at the center of the tool, but we have a filterable list of the hits at the right, which display alignments and details when the hit is selected. And at the left, we have the hit stack. Okay? The most significant issue, though, is the ability to fetch BLAST results on demand using web service calls. So if I start with a single query and I get a bunch of matches, and I decide that what I would really like to do is to go exploring the hit landscape, if you like, then I can click on one of those particular nodes and have the map reorganize, and we'll have this period of interregnum where nothing much is happening, but then eventually the web services will respond and the map will reorganize and we'll get a new display and we'll see the new landscape. So this enables us to explore the hit space, but most importantly, once we've got this, we're able to share the collection with colleagues and the community, because we can capture the collection that we have, we can capture the view, and we can share it. So we'll move on now to a case study on exon skipping. Okay, and so this is a bit of reverse engineering in a way. This is a recent paper which is in Press in Leukemia Research, alternative splicing of HMLH1 in childhood acute, etc. Okay, the point here is that we're looking at a phenomenon known as mismatch repair deficiency. And mismatch repair deficiency is a common feature of certain types of leukemia. And essentially, if we disable or interfere with mismatch repair, then we have some ability to cause an awful lot of grief for the cell line. And this is characteristic of some forms of leukemia. So one potential mechanism for the failure of the mismatch repair functionality is a splicing failure. And so what happens in this situation is that certain exons get skipped over during translation. And so we see an assembly of what's essentially a gene, but it's a gene which is incomplete, and it produces different proteins. And this is something that we're going to explore a little. So if exons are skipped, we get this incomplete gene which may still be assembled, it may still be translated, we still get a product protein, but that product protein is not typically very, very helpful for the organism that results. And the hypothesis, of course, was that cancer trends may be associated with the isoforms of this particular gene. So to use the BLAST Explorer to deal with this, or to investigate this sort of problem, we begin by taking this sequence protein. Okay, we tailor the search space and the thresholds. So we'll go searching in the taxon of Homo sapiens. We'll set an E-value of 1. And then we'll go and infer the relationships and the morphology which result. And we'll do this live. Okay, so this is SilverMap in the BLAST Explorer configuration. We open up the collection. Okay, and we'll go here, which is... okay, thank you. That may be a little bit troublesome later on, but anyway, we'll see what we can do. So this yields us the accession ID, which is helpfully pre-populated. We'll reset the E-value cutoff to 1. We'll go to the taxon. We'll type in Homo, and we'll get Homo sapiens. We could actually have the Neanderthals as well, but we'll leave that today. And at that point, we'll open. Thank you for that. Okay, we should still just be able to filter. Okay, so what we see, let me just make this slightly smaller just to show you what's happening on the left-hand side there. So I'll maximize it again, or at least drag it out so that we can get the best view that we can. So as in the discussion before, what we see over here is the top hits, okay, which we're then able to filter based on e-value and a variety of other things. And the easiest way of doing that is to do that graphically, and I'll show you that in a moment. What we have on the left-hand side is that we have, once we executed the query, we got two blasts being generated. The first blast at the top there compared the query protein against a conserved domain database, and those are the results which are returned, and that's significant for us, as we'll see in a moment. And down here we have the hits from the Homo sapiens taxon. Okay? Over at the right-hand side, as you can see, you've just got the list of the resulting hits. What we'll do to begin with is that we'll have a bit of a look at what's at the center. Let me just try and do a little bit of dragging. That's probably as good as I'm going to do. And so what I can do at the center here, this allows us to threshold. This is the tab to move that radius. So what I'll do is I'll just go to about there, and at that point I'll select here, show only the items within radius, and we'll see that we reduce our list to the set that we want to work with. A couple of points to note here. In the display, what you see are two different types of node. You have the circular nodes, which are the hits from the Homo sapiens taxon. The square nodes represent the ones from the conserved domain database. Now, what we're most interested in at the moment, then, is the overlap from the conserved domains across the hits which come back from the NCBI database. And by control-clicking on these particular domains, we're able to overlay these responses across the results that we see down the bottom there. And immediately, based on the top scores that we see, we're able to deduce that there's a certain problem in this sort of region around here, okay? And it's kind of helpful at this point. Let's just get rid of those overlays because we can kind of infer them by eye anyway at this stage, having seen them. But it's kind of helpful to note that one of the matches with helpfully an e-value of 0 is, sorry, the tooltip let me down. Okay, is the HMLH1 gene product, which is, of course, the query. And so that tells us that we're sort of in the right territory. Now, that also allows us to infer that we've got a problem with these particular proteins which have come back. Okay? So a couple of things that we're able to do from this point. The first one is that by clicking on any of the matches in the hit stack, we start to get the results over on the right-hand side here, okay, from the actual BLAST query. And, of course, the map has reorganized itself to make that particular node the most prominent. And we see that on the map itself at the present time. The other thing to note is that if we wish to, we can move around and have a closer look at some of these particular protein results. We're also able to have a bit of a click and have a look at another particular node, okay? And this one, of course, has two hits. And we see over here that the results over here show us the two separate alignments coming back from the BLAST queries. So we're able to get very detailed information about what's going on in the organization, okay? If I wish to recover at any stage the original position, I'm able to do that by looking at the query at the top. I'll come back to that in a second. But one of the things which I'm also able to do, as I said before, is to decide, well, I'm going to have a closer look at the hit space, and I'm really interested in the hit space around this particular gene, this particular protein here. And so what we'll do is we will organize this and scroll out a little. And that's the result of real-time blasts that went off while I was adjusting the display. Okay? What happens, which I didn't scroll enough to show you in time, is that you have this initial situation with the query node at the center, and then all the other nodes just sitting on the periphery as though they're at infinity, awaiting the blast results. And as the blast results come back, then they create an appropriate map. Now, the other aspect about this, which is worth noting, is the fact that I have a bunch of queries. I've done one query, okay? This is the unnamed protein product. I also have my original query, which was that one, and I'm able to recover that straightforwardly. The map will reload by just going back to the toggle box. So those are cached and saved and can be reused. One other thing which I should probably mention I'll just select one of these. I haven't actually tried this one, so I don't know what's actually there with it, but I'm also able to go off and get information from a GenBank associated with those particular records. So all of that information is available to me at my fingertips. The navigation is never destroyed by the fact that I have to jump between different web pages, and I have a synchronized view of all of these things at a given time. And yes, I'm certainly able to see by looking at the results of some of the particular proteins which we observed that the conserved domains that are missing are very, very important indeed, because they have some well-known function associated with DNA mismatch repair. And of course, that's the problem that we were seeking to address or examine in some respect. So we come back to the PowerPoint, and that was our live demo. And that's a summary of what we observed. The top 13 hits showing protein isoforms of varying lengths and differential conservation. The important point with these particular families were disrupted in those particular isoforms, meaning that their function in support of mismatch repair was basically not there. So we're able to rapidly identify a set of isoforms implicated in a particular disease and use those as a basis for further investigation. So some of the advantages of the BLAST Explorer. The main thing about it is that it allows us to explore what I've called the hit landscape, the domain, if you like. It allows simple and convenient secondary blasts. I begin with one simple blast query, but if I want to examine what's going on around it, then I'm able to very rapidly do that and see how the new topological organization, if you like, actually is, without having to trawl through a large amount of BLAST printouts. The exploratory result sets are cumulative. We have them cached, and so we can flip between them, as we've seen. And also the alignment stack, the map and hit details are synchronized. So we sort of never lose track, or very seldom lose track, of where we are on the page. Application extensions. A couple of points about the way the BLAST Explorer and SilverMap in general has been architected. It's got a flexible interface-based design through iObject model and iData provider. We've tried as far as possible to be agnostic with respect to the data sources which come into the tool, and to provide pathways for people to configure the tool to work with their particular data sets. So iObject model gives us application-specific node content. iData provider gives us view-specific and purpose-specific approaches for getting the data into the nodes. In addition, we have alternative ways of doing page layout, but most importantly, the iSilverMap adapter gives us a lot of control and uses a lot of control in respect of low-level customization. In particular, the facility to provide their own similarity measure, okay, so that it can be extended for use for similarity measures that are not based on BLAST. And that was a key design goal right from the start. The future. At present, we're looking at extending the BLAST capabilities to other databases, providers, and of course providing a raw sequence entry window so that it mimics all of the usual capacities of BLAST. Better focus on input and output of BLAST results, in particular the facility for loading up large collections of BLAST results so that people can explore domains with which they are familiar. And also looking at exchange with other tools, in particular sequence alignment viewers and Excel. Okay, so we're very much looking to try and integrate what we do with some of the other tools which are part of the ecosystem. And finally, we are working actively at the present time on semantic integration with the Bio2RDF project, which of course provides RDF-based views of some of the major databases like GenBank and SwissProt and PubMed. So to conclude, the usual contact details. Okay, we have a Codeplex site which is under construction, but we will be releasing this in a slightly modified form, in other words, a slightly cleaned up form around the end of October, but please contact me if you wish for earlier access than that. And I'd like to have acknowledgements of the sponsors, but more importantly, or just as importantly, I'd like to acknowledge Lawrence Buckingham, who's here today, who did most of the programming, and another member of our team called Scott Mann, who worked up the example on leukemia for us. Are there any questions?
Actually, I'm not sure if I need this or not, but I'll talk into it. When you were clicking around on the BLAST Explorer and it sort of drifts out and drifts back in and the different points come in, are you seeing bidirectional BLAST results? So are you seeing
No, they're these are unidirectional BLAST results displayed, but each time I double click on one of these, sorry, what happened then? I got a label, sorry, I didn't get a node. So what happens there, you start off with that because there are no BLAST results associated with that particular node, and that's gone off and hit the NCBI web services and has come back and, they're real BLAST results. So if you want to convert it to work with bidirectional BLAST results, then that's something that you can do, but that's not the similarity measure there that's in place at the moment. Rather, what's happening is you're getting unidirectional results, and you're producing them on the fly.
Okay. Thank you.
Okay. Okay, thank you very much.